Okay, so in continuing with the notion of determinant, one of the most important ideas is if I can write a system in the form AX equals B, if A is n by n. If A is n by n, then I can potentially have a unique solution. Okay? So there's a whole bunch of things in our set of equivalent conditions. So we say that there's a unique solution to this if and only if A inverse exists, which is if and only if A is non-singular, which is if and only if A can be written as a product of elementary matrices, if and only if A can be row reduced to the identity matrix. And remember, those same steps would take the identity and reduce it to the A inverse. We're going to get into things about the rows and columns of A in chapter 4. There are several more things in our set of equivalent conditions. But the reason we love that, this list is going to get long, is the fact that they're called equivalent conditions means if any one of them is true, they're all true. If any one of them is false, they're all false. So if I need to prove something, and in order to prove it, I need this concept here, but there's 10 equivalent conditions, and I can easily show this one over here, I get all of them. And that's kind of where a lot of this is going to be going. So the first major use of a determinant is determining if this has a unique solution. So rather than trying to find A inverse or even doing all my row operations, maybe I want to do this on a computer. Problem is, if this doesn't have a unique solution, there is no software that will give you an answer. In other words, if this was inconsistent, that might cause the computer to smoke and then the tilt sign flips up, you know, the whole thing. Or if it has a dependent, so you can't parameterize that way. So I want to know if this has a unique solution, so probably the first fastest way is simply to find the determinant. Now, what if this is a really, really large system? Can I have a computer find a determinant? Yes, because there's exactly one value. That's not abstract. That's every n by n matrix has exactly one value that serves as the determinant. That's it. Okay? So that's an easy thing. Now, the determinant is either what or what?
0 or not 0.
0 or not 0. I don't care what the number is if it's not 0. Okay? Do I got all the quizzes? You're not still working on it, right?
I'm starting my name on.
Okay. Yes. So rapidly writing. Yeah, you want to get that thing in. Okay, so first thing I want to go over.
Would a complex number fall under the not 0?
Yes.
Camp?
Yeah, it's still, because 0 is still technically a complex number. It's 0 plus 0i. That's a great question. That comes up later. In fact, that comes up in this course at the very, very end. So it's a non-concern right now, but it still applies if I have a matrix of complex numbers. It's still 0 or it's not 0. And that's comforting that that doesn't change. So I want to talk about one of the really, really important results, and I want to do a demonstration of it. Let's say A is 2, negative 3, how about 2, or not, I'm sorry, negative 2, 4. Okay, keep it simple. And B is negative 1, 2, 3, 8. All right. Let's find each of the following. I want to find the determinant of A, the determinant of B. I want to find A inverse, and I want to find AB. I want to find the determinant of A inverse, and I want to find the determinant of AB. This is an exercise, so we're going to do a little, I'm doing 2 by 2s to make this easy. But we know what the result's going to be because I told you last day, but then we're going to prove it. And it's important that we understand the proof is not complicated, but we kind of have to prove it. I can't just say, oh, here's the result, trust me. Not if I can show you the result. So let's start with this. So the determinant of A, so that would be 2, negative 3, negative 2, 4. So that would be 8 minus 6, or 2. The determinant of B, so that's negative 1, 2, 3, 8. So that's negative 8 minus 6, or negative 14. Okay, got that. Now, what is A inverse? A inverse would be, okay, 8 minus 6. We already know it's going to be 1 over the determinant, right? Times, now we rearrange things appropriately, 4, 2, 2, 3, so that's 2 3/2, 1 1. The determinant of A inverse is then 2 minus 3/2 or 1/2. Okay? AB. So let's do AB. So we're going to have -2, -9 is -11. Then I'm going to have 4 minus 24, that's -20. Then I'm going to have, hold on, okay, try not to pull a muscle doing this way. 2 plus 12, that's 14. And then finally, -4 plus 32, that's 28. Did I get that right? Doing this at an angle. Okay, actually, while we're at it, let's do BA. Oh, just for that, let's do BA. Okay, so that would be -2, -4, so that's -6. And then I'll have 3 plus 8, that's 11. Then I'll have 6 minus 16, if I did this correctly. And then finally, -9 plus 32. All right, does that look correct? Everybody cool with that? Okay. Now, the last things I want to find. What is the determinant? We already found that guy. What is the determinant of AB? So that'd be -308 plus 280, that's -28. What's the determinant of BA? So that'd be -138 plus 110. Huh. Well, that's interesting. AB and BA are absolutely not equal. But their determinants are. Huh, go figure. What is the determinant of A times the determinant of B? -28? That's real number multiplication. Real number multiplication is commutative. Matrix multiplication is not commutative. Isn't that interesting? We wouldn't even have thought that the determinant of AB is the same as the determinant of BA, even though AB is not equal to BA, because in both cases they end up being the product. What do you notice about the determinant of the inverse? It's the reciprocal of the determinant of A, and so on. Now, I'm going to do the proof. The proof's actually really, really simple. If you look in the text, the author doesn't actually do the proof, he just sort of talks you through it, because it's just not complicated. And it goes back to, there are exactly 3 elementary row operations that are legal. A row switch, multiplying a row by a scalar, and using a multiple of a pivot to add to another row. But what did we prove in class? That the row switch changes the determinant by a factor of -1, and multiplying a row by a scalar increases the determinant by exactly that scalar. So, if I wanted to take A and write it as, we know it's the product of the inverses of elementary matrices. So let me just call my elementary matrices, how about, I don't know, M1, M2, up to Mn. Let's just call it that, okay? These are my elementary matrices that A is going to equal the product of. But we know that each elementary matrix, right, is going to change the determinant, and that's why we use the inverse. Remember when we talked about if you're doing a row operation, you keep track of the change if you did a row switch or you multiply a row by a scalar. So an easy way to think about it is like this. Let me take a simple matrix A, say 2, -4, 3, 7. The first step you'd probably want to do is multiply row 1 by half. Remember, we want to make it look like the identity at some point. So my E1, if you will, what's E1? E1 would be 1/2, 0, 0, because I multiplied row 1 by a half.
Should it be a 1 in
Did I?
2, 2? Or
Oh, thank you, thank you. There's a 1 there. So what is E1 inverse?
2, 0, 0?
That'd be 2, 0, 0, 1. And so I know if I take E1 and I multiply it by A, I will get this. And by multiplying E1 by A, what did I do to the determinant? I multiplied row 1 by a half. I know I reduced the determinant by a half. So what do? We factored the 2 out in front. But in the end, when I write what A equals, it's going to be this matrix times the next matrix times the next matrix and so on. So it turns out A is going to be the product of elementary matrices, each elementary matrix being the inverse of the step I did. So when I multiplied by a scalar, I multiply by the reciprocal of the scalar. When I do a row switch, I do a row switch. When I use a multiple of a pivot, I use multiple of a pivot. But in the end, since A is going to equal E1 inverse times E, let's say K inverse, not all of those are going to have a determinant that's different from 1. Remember when you did a multiple of a pivot and you added it to another row? It didn't change the determinant. So every time I do that, I'm still going to get a determinant of 1. The only elementary matrices that change the value of the determinant are the row switch and multiplying by a scalar. But the scalars are always evidenced in here. So we then know that the determinant of A, of course, is the determinant of these guys, yes. Oops. But it's also equal to the individual determinants. And again, because if I used a pivot, the determinant is still 1. That didn't change it. When I multiplied by a scalar, the reciprocal of that scalar is right here. So the value of this determinant is, in fact, 2. Okay? And when I do a row switch, the value of that determinant is, in fact, -1. So because A can be broken down into the product of elementary matrices, and the product of the determinants will always be A because only the row switches and the multiplying by scalars change it, and I take all of those into account when I do it, then in general, since every matrix can be broken down into the product of elementary matrices, I can say the determinant of a matrix is the product of the determinants of the elementary matrices. So therefore, if I want to multiply 2 matrices together, the individual matrices are still the product of the original elementary matrices. It would be a really long-looking problem. But because it's still the product of elementary matrices, therefore the determinants are still the product of their determinants, I get the original matrices. So that means for n by n, A, B, because this can be written as the product of elementary matrices, and so can this, and I have this really long string of elementary matrices, I'm still going to get the same numerical values because I'm basically just using parentheses, associative property. Okay? That's a very powerful one, but that also therefore leads to that if I take a matrix and I multiply it by its inverse, I get the identity. But the determinant of the identity, being a triangular matrix, is the product of 1s. So that means the determinant of an inverse matrix is the reciprocal of the determinant of the original. That's where that comes from. What if I want to take a matrix and raise it to a power? What would that do to its determinant? The determinant of the power. I want to take this A and raise it to the 10th power. What would the determinant of that be? The determinant to the 10th power, exactly. That should make perfect sense. Does that, everybody okay with that? So those are properties that are really powerful and really cool, and you will utilize them over time, okay? So now, that's not an application, that's just a rule of matrices in general with their determinants. Now, I want you to consider, sorry, simple problem, all right? Baby algebra. I've got 2 points. Okay? And I want to find the equation of the line passing through these 2 points. It's a fairly simple thing. We know to use the point slope formula. Agreed? What's the slope? It'll be the change in y over the change in x. And we know the point slope formula is x minus, now, which point should I use? The answer is yes. Because if I use the first point and then use the slope, I get to the second point and vice versa. It never matters which point you use, you're always going to get the same answer as long as you calculate the slope correctly. We know this. So let's say I use the first point. We know this. I'm sorry, I've got backwards. Sorry, y minus y1. Y minus y1 is slope x minus x1. We know that's the point slope formula. But I don't want to write it in that form. I'm going to write it using that. So I'm going to write it as y minus y1 equals this. Because that's exactly the same thing, isn't it? Okay? Let's multiply both sides by x2 minus x1. And that would have x2 minus x1 times y minus y1 equals y2 minus y1 times x minus x1. I know this is true, okay? And the idea being the individual points that are given, x1, x2, y1, and y2, we know are constants. Those are not variables. Those are given values. The x and the y are variables. So therefore, any combination of x's and y's that makes this true, we know how that works. Any x and y that makes this true must be a point on this line. Great. So it's constant, constant, variable, constant, 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 variable, constant. Okay. Let's multiply this out. See, I'm kind of taking the point slope formula and undoing it. I'm breaking it down. I'm going backward, which is crazy. So x2y minus x2y1 minus x1y plus x1y1 equals, I'll keep it in the same order, xy2 minus x1y2 minus xy1 plus x1y1. Now, part of the reason it did not matter that I used the first point or the second point, does anybody notice anything? The only things that cancel are the product of the coordinates of the first point. Had I used the second point, that's what would have canceled. Okay, now just for the heck of it, let's throw everything on the same side for no good reason. x2y minus x2y1 minus x1y minus xy2 plus x1y2 plus xy1. I think I did this right. Okay. What does this all equal? 0. Boy, I'm really making the point slope formula complicated, aren't I? What do you see? You see 6 different products in a sum, half of them positive, half of them negative. Have we seen this movie before? What else did we look at recently where it was 6 terms in a product, half of them positive, half of them negative? Go in, get in your Wayback Machine. Go to, I don't know, Wednesday's class last week.
The determinant?
Very specifically, which determinant?
Of a 3-dimension?
Of a 3 by 3. Didn't we show that the result of the determinant of a 3 by 3, remember we used ABC, 1, 2, 3? Do you remember we got 6 terms with ABCs and all meant different 1, 2, 3s? Huh, that's kind of interesting, isn't it? Except I don't have a product here of, obviously, I don't have a product of 3 things. Yeah, I do. You don't see it? What's my third thing in each term? There. Now I have a product of 3 things. This is a determinant now. So you say, you used the same number 3 times? No, I didn't. That's 1, 1, that's 1, 2, and that's 1, 3. You know, with subscripts, if you want to do it that way. Huh. Well, Can I make this work? I can. This is equal to this. That is crazy. And this equals 0. These are all constants. These are variables. There's an infinite number of ordered pairs on the line. Do you agree? Only the combinations of x, y that are on the line would make this determinant 0. Okay? So let's have some fun with this, shall we? Because that's our primary goal today. Having fun with determinants. That should be the name of this lecture. All right. So let's suppose I gave you the points -1, 3, excuse me, and I don't know, how about 3, 9? And I want to find an equation of the line that passes through these 2 points. So let's do it this way. All we do is put x, y, 1, negative 1, 3, 1, 3, 9, 1. It doesn't matter which row or column I expand by. So in this orientation, what do you think is probably the simplest one to look at? Any row or column will work.
The one.
Yeah, I'd probably go for the ones. It's just, yeah. So if I go for the last column, plus, minus, this is in the plus position. So I'd have, this is, if you want, 1 times negative 9 minus 9. That's negative 18. Minus 1 times 9x minus 3y. Okay. Plus 1 times 3x plus y. And that's all supposed to equal 0. That equals 0 is actually quite important. Okay, let's clean this up a bit. I'd have negative 18 minus 9x plus 3y plus 3x plus y equals 0. So that would give me negative 6x plus 4y minus 18 equals 0. Is this an equation of the line? Yeah. Is it the most useful form? I don't know. Most of us would like slope-intercept form probably. But is this an equation? Yes, it is. If I solve for y, my life might be a little bit easier. So if I write 4y equals, I'd have positive 6x plus 18. So y would be 3 halves x plus 9 halves. Okay? Let's go back to here. What's the slope?
3 halves.
6/4 or 3 halves. So you would have said y minus 9 equals 3 halves x minus 3. And I think we would have got the same answer in the end. So we found a way to find the equation of a line. Boy, was that long-winded. Okay, why in the world would I ever want to do that? Probably wouldn't want to do it that way. Probably not practical. What am I asking you? No, what am I asking? What is that?
You're asking, well,
Are they on the same line?
Are they on the same line? That's what collinear means. Oh, that's easy. Let me take the first two, find the slope between them, find the equation of the line, and then take the third one and plug it into the equation of the line to see if it satisfies the equation of the line. That's what we would all do. I'm too lazy to do that. It takes too long. That's about 5 times as many steps as that. But wait a minute, aren't I doing the same thing? No. What did we say about xy? Every xy that is on the line makes this equal to 0. So take all 3 points, put them in here. Your result is either 0 or it is not. If it's 0, they're collinear. If it's not, they're not collinear. You like that idea? Yeah. By the way, way faster. So what do I? Because you'll be done with the determinant before you would have found the equation of the first line, and then having to take points and substituting it in. A lot of algebra. So let's do that. By the way, does it matter what order I put them in?
No.
Because if the determinant equals 0, then no row operation I perform will change the 0. Isn't that cool? Row switch is -1 times your 0. Using a pivot is still 1 times your 0. Multiplying a row by a scalar is the scalar times 0. If the determinant is 0, then no row operation will change that. That's a good thing, by the way. If my determinant is not 0, then row operations may change it, but I don't need to do any row operations. Actually, I think I do want to do row operations. I got those ones just sitting there. Why don't I pick one of these to be my pivot? Does it matter which one? No. Which one do you want to use, Zachary?
Top.
Okay, let's use that one. Let's put zeros below it. So let's take negative row 1 plus row 2. Let's take negative row 1 plus row 3. And I'm putting an equal sign because that we know that is an operation that will not change the determinant, 0 or not 0. So the negative of that, the negative of that, the negative of that, the negative of that, plus minus plus. Can I evaluate the determinant without rewriting the entire problem as something times a 2 by 2? Can I do that? Because what are you doing now? Aren't you just doing that problem? Times positive 1? Does everybody understand? I don't need to write, and this equals 1 times the 2 by 2. That's a correct mathematical statement. It is 1 times the 2 by 2. So why don't I just evaluate the 2 by 2? And what am I going to get? Negative 6 minus negative 16. If it helps. And that's not 0. Cool. I got 10. Now, if this were Calc 3, what we would do is we would form a couple of vectors, a PQ and a PR. We'd probably find a cross product. We'd do a whole bunch of stuff, and eventually we'd get an answer, and everything we said was correct, but boy, it would be a lot of work. Are they collinear? No. If they're not collinear, this is kind of a cool little follow-up. It's sort of a natural thing. I have 3 points, and they're not collinear. Now, if you remember from Calculus 3, for those in Calculus 3, those 3 non-collinear points uniquely determine a what?
Plane.
What's that shape? It's supposed to be
Parallelogram.
a parallelogram. What do you suppose the 10 is? It's the area of the parallelogram. It is the area of the parallelogram. And you can prove that by using cross product, but it's way more work.
So that determinant is equal to the magnitude of the cross product?
I'm sorry, please.
Is that determinant equal to the magnitude of the cross product?
In this case, yes. Plus or minus. Do you agree that the order I put the points in was arbitrary? And there's 3 factorial ways, 6 ways I could have put the points in. Half of them would have given me 10, half of them would have given me negative 10. We have to remember that. Oh, okay. So technically it's the absolute value of my determinant, which seems weird. Don't put absolute values on your determinant, please. Yeah, there's no double bars. My determinant is going to be negative exactly 50% of the time, positive 50% of the time, because of the arbitrary nature of putting the points in. So if that determinant happened to be negative 10, then we'd say 10 is the area. Okay, so it's the absolute value of this would be the magnitude of the cross product. Now, I'm only saying that we're not doing cross product. Okay, in fact, if you haven't had Calc 3 at all, that term would mean nothing to you. Unrelated to what we're doing. Is that kind of cool though? Now, what if I only wanted the area of the triangle that these guys uniquely determine? Yeah, yeah. Oh, okay, that's like an oh duh. Yeah, that's kind of cool, that's kind of neat, but you know, I kind of prefer the old way of doing things. That's awesome. All right, yeah, that's great. Here's 3 points in space. Let's assume they are not collinear. I have 3 points in space. How many planes can these 3 points live on? Exactly 1. There'd be a unique plane. Okay, we know that again, that's a Calc 3 thing. We know exactly how to find the equation of that plane. If you're in my Calc 3 class, we call the first point P, we call the second point Q, we call the third point R, we make 2 vectors, PQ and PR, we find the cross product, find the normal vector, we then perform the dot product with that, with x minus x. You go, yeah, we nailed that in Calc 3, that's on the test next week, and that's all correct. I think there might be an easier way. Same thing. If I give you 3 points in space and you want to find the equation of the plane they all live on, it's exactly the same thing we just did. I'm not going to go through the derivation because that'll take us a half an hour. I've done it before. It takes too long. If I do the PQ, PR, cross product, normal vector, do through the entire thing, we'll get an answer, and I'm going to have x1, x2s, x3s, y1, y2, y, all over the place. We already know that. But in the end, what you're going to see are 24 terms with products of x, y's, and z's. And then I'm going to throw the ones on there and show you, and 12 of them will be positive, 12 will be negative. We know it came from a 4x4 determinant. It came from this. If I evaluate this determinant, now think about that. 4x4, that's a lot of work. Yeah, it is. It's not a fast process, but it's a correct process. If I evaluate this 4x4 determinant, set it equal to 0, only the points that are on the plane can satisfy that. So there will be something with an x, y, and z in it. Now, the calculus approach is still the best way, because most of you can do the calculus approach, finding the normal vector. Right? How many know that approach? And you probably can do it fairly fast. So, by the way, was this a fast way to find the equation of a line? Oh, heck no. What was it better for? What's it better for?
Whether or not it's.
All right. Oh, I just found in my pocket point number 4. I'd really like to know if point number 4 is on the plane those other 3 are. Now, the calculus approach. You find your 2 vectors, you take the cross product, you find the normal vector, you find the equation of the plane, simplify it all out, and then take the 4th one and plug it in, and either it's satisfied or it don't. And if you're really fast, you can probably do that in 10 minutes, if you're really fast. Or, this is 0 or it's not. And because these are all constants, I would do some row operations, and I'll be done with this problem in 30 seconds. 45 if I got the TV on. You like that? Yeah, infinitely faster. So you know what I put on my calculus tests? I give you a 4th point and say, is it on the equation of the plane? You can't use linear algebra to answer this. Because anybody who's had linear algebra is going to do this 100% of the time because it's probably 10% of the work. Yeah, you can use a determinant to determine if 4 points in space are coplanar. Really? Yeah. Yeah, in the same way I can determine if 3 points on the plane are collinear. I mean, you gotta admit, that's kind of cool. And there's no part of this process that's difficult because these are all really nice values. And can I do row operations to make this smaller? Yeah, in fact, I should do row operations to make this smaller. These are all constants. So I probably, like Zachary said before, take the 1, make a column of zeros, now I have a 3x3. I can choose to evaluate that, or I can choose to keep going. That's your choice. It's whatever you feel you're faster at. But this is a really, really nice use of a determinant as an application. You're using the determinant as a tool to answer a question that's not even related. I mean, lines on the plane, planes in space, I can use a determinant to answer these questions. Yeah, in fact, it's faster if I'm trying to determine collinearity or coplanar. Crazy. Do you agree? Completely out of control. Okay, next one. This is a simple one. This is one we've all done sometime in our lives. Okay? We now know there are multiple ways to solve this. In baby algebra, the first way, we graphed these 2 lines. If they intersected, we read the point of intersection. The reason that is flawed in general is it only works if the intersection are integer values and relatively small integer values. So I'm going to graph it. It turns out the intersection is 3,947, 16,135. So I need a really big piece of graph paper to, See, it only works if my integer values are literally single digit. Do you agree? If they're fractional, forget it. So graphing is not the best way. It's the first way. So then we use the substitution or the addition method. This is perfect for the addition method. That's where we take a multiple of 1, add it to the other, eliminate a variable. Substitutions, we solve for one variable and then substitute it into the other equation. Those are about the same amount of work. Now we're linear algebra folk. We can use a matrix. We can find the inverse of the coefficient matrix and multiply. Those are absolutely valid ways. So now we're gonna go over the sixth method. Okay, the only one we haven't looked at. So let's do this first of all using the addition method. So I want to get rid of the y's first, because I want to solve for x. So to get rid of the y's, I need to multiply each equation by something. So let's take, I'm getting rid of the y's. So let's multiply this equation by a. Okay. Did I say the? No, I'm sorry. I said I'm getting rid of the x's. Sorry, I'm looking at one. That's not the x's. Now let's take this equation times negative c. I think that I wrote that correctly. Yeah. So when I do that, what do I get now? I get negative acx, negative bcy equals negative ce. I'll keep things in alphabetical order. Just keeps easier to keep track of. Then acx plus ady equals af. And when I add those together, that's gone. These are coefficients, so I'll write it as AD minus BC times Y equals AF minus CE. So Y equals AF minus CE, AD minus BC. Now, that's either an integer or a fraction. I mean, that's not complicated. Now let's do the same thing. And this time let's cancel the y's. That's what I meant to do the first time. I just got crazy for a moment. So I've got ax plus by equals e. I have cx plus dy equals f. So now I want to get rid of the y's, so I need to multiply by the appropriate term. So let's multiply this one by d, and this one by negative b. Okay, so that gives me the new system ADX plus BDY equals DE, negative BCX, negative BDY equals negative BF, and when I add those together, I'm going to get AD minus BC times X equals DE minus BF. So ultimately X equals DE minus BF over AD minus BC. I gave you a random system of two variables and two equations. Let's assume for a moment there actually is a unique solution. Let's just assume that for a moment. I've just done a formal mathematical proof that says anytime you're solving a system of two variables, and this is actually true for, doesn't matter how many variables. If I have a unique solution, they always have the same denominator. But wait a minute, I sometimes have an integer comma fraction, or I have two different fractions. Yeah, you had 3/12 comma 4/12. And you reduced your fractions to 1/4 comma 1/3. But in actuality, you always have the same denominator. You can choose to reduce it, but you always have the same denominator. You can't have different denominators when you're starting off. Oh, okay, it's the reduction that changes things. Now, that denominator is kind of obvious where that came from. If I wrote this as a matrix, wouldn't I have written it like this? Do you agree that's what we would have written? And we know how to solve that using an inverse. So look at my denominators. What are my denominators, clearly? They're the determinants of the coefficient matrix. That's hopefully, pretty close to an O duh. But look at the form of the denominator, product minus product. Look at your numerators. They're exactly the same form. Could my numerators also be a determinant? I think that is sort of like the overriding theme today. So the answer would be yes, of course they are. But what determinant would they be? Let's see if we can figure it out. Clearly, my numerators look just like my denominators in terms of their form. So I'm going to write it this way. I'm going to say x equals the determinant of a, b, c, d. And I'm going to put another determinant there. And I'm going to say y is this. Now remember, I put all the letters in alphabetical order, lest we forget. So Oops, sorry, wrong place. What has to go here to make it work?
Wait, oh, sorry.
Look at your numerator, look, X. Have to put a BB there, wouldn't I? Huh. What would I have to put here to make this work? Probably AC. Huh, that's kind of interesting. So go back to the system that I started with. Let me do this. Let me erase all the peripheral stuff here. This is the system that I started with. It's kind of obvious now. My denominator is clearly the determinant of the coefficient matrix. Now look at my numerator. It's the same as the denominator, but I replaced the first column, which were the coefficients of x, with the EF that's on the right. And for y, what did I do? I replaced the y column with the EF on the right. Huh. That's kind of interesting. If this has a unique solution, then this is the solution. Are there potential problems here? Yeah, what if? What if my denominator actually is 0? Then that means there's no unique solution. We're going to look at that, what that looks like. That means either it's inconsistent or it's dependent, but there's no unique solution. That's what that tells me. This is a formula. My answer is x comma y. This is called Cramer's rule. I'm sure most of you learned this as babies in algebra, but you probably don't remember anything about it. Cramer's rule is how I can solve a system of equations using determinants rather than matrices. Is it faster? For a 2 by 2, it can actually be the fastest way there is. I'm going to show you that. For a 2 by 2. All right. I'm going to show you how ridiculously fast you can do this process. All right, I've got 11x minus 13y equals negative 7, and I've got 8x plus 5y equals 13. Do you want to use substitution? That's where you solve for one variable and substitute the other. Oh, heck no. Boy, talk about messy algebra. You can use the addition method. That's you take a multiple of one, add to multiple of the other, cancel. Take that solution and substitute it in, or just do it again. You probably do it again. Or I can do this. So when I do this, there's a simple format that most people follow. I'm going to name my determinants. And I'm going to name them like this. D for determinant. D is going to be the determinant of the coefficient matrix, which would be 11, negative 13, 8, 5. Now, dx, that's going to be the numerator of the x variable solution. How do I get it? I copy down the same determinant, but I change that first column to these numbers. Then I call the third one dy, which would be the numerator of the y solution. Again, I'm going back to this, and now I replace the y column with the constants. I always do it by stacking the determinants, so it's easier for me to identify where the changes come from. When we do this for a 3 by 3, a 4 by 4, a 5 by 5, which you actually can, you're only changing one column. Everything looks like this, but you change one column. Which column? Specifically the one that goes with that particular variable. And you change it to those constants. It's harder to see that in the 2 by 2. It's much easier in the 3 by 3 to say, oh, I'm going to do this 3 times. Yes. Now, let's calculate these. So that's 55 plus 104, which is 159. This is negative 35 plus 169, which is 134. This is 143 plus 56, which is 199. So what's the answer? It's 134 over 159, 199 over 159. Would you say the answer is hideous? For a 2 by 2, would you say that's about as awful as you've ever seen? Yeah. what part of this process was difficult or awful or used icky numbers? In other words, I guarantee you, no matter how fast you are, this is the fastest way to do this problem, especially when the numbers are icky. You like that? Now, if I gave you a 3-variable 3 equation problem, this is the longest way humanly possible to solve the problem. You just evaluate 3 2x2s, no matter how ugly the numbers were, this is trivial. I don't care how big the numbers are, you can have a calculator in your hand to do it. And you're representing your answers as quotients of those integer values. Not decimals, quotients of the integer values. If this had been 3 equations and 3 variables, now you have 4 3x3 determinants that you have to evaluate. Ooh. If this were 4 variables in 4 equations, now you have 5 4x4s. No, use a matrix. Way faster. So what's the advantage of using Cramer's rule? This was my answer. Don't I want this answer, not decimals? If I do row operations using a matrix on a computer, and I say I want row operations, I'm going to get decimal equivalents of these, and they're probably off. However many decimals you report, the last one will be off, because it used decimals to get there, because the first step would have been to multiply through by 1/11. And then I use those decimal values. You have to understand the flaw in that, it's horrible. So computers don't do row operations when they do a matrix solution. They do this. So if a computer, how do you know that? How many have a graphing calculator and you've actually done a matrix problem on your graphing calculator? Did you get fractional solutions? Yeah. Then it didn't do row operations. That's not possible. There's no human being who's even attempted to program a matrix to preserve fractions. They have to convert things to real numbers. Anybody who's done programming understands this. You have 2 choices, integers or real numbers. Fractions isn't one of them, by the way. There's no computer program that will do fractions, real numbers, and decimals, and integers. So you program the computer to do this. And then you report your answer literally as text, numerator, denominator. It's reporting your answer. It's not even storing this as a number. It's really storing it as a symbol over a symbol. Now you gotta admit, that's kind of cool. Whoever figured that out, that was very clever. How do I know? Because when I started teaching linear algebra, 100% of calculator answers were incorrect. 100%. Because they gave decimal round-offs to simple fractions. I mean, 1/3 wasn't even 0.33. It was usually like 0.34 or 0.32 because of the previous errors in round-off and using, it's called accumulated round-off error. There are courses you take as an engineer, learning how to deal with that sort of thing. But we completely eliminate it if we do this. Now, is it practical for you to do Cramer's rule by hand on a large problem? Oh, heck no. Not practical at all. But if I was programming the computer and I knew I had a unique solution, it's awesome. Now, what about let me do a really simple one. I have x plus 2y is 6, 2x plus 4y is 12. Do you recognize something about this problem? It's the same equation twice. So shouldn't I get a dependent system? Let's use Cramer's rule. Cramer's rule is awesome when there's a unique solution. Using an inverse is awesome when there's a unique solution. Using a matrix is awesome when there's a unique solution. Problem is, you have no control. We suspect is not going to have a unique solution. So my D is 1, 2, 2, 4. My dx is 6, 12, 2, 4. And my dy is 1, 2, 6, 12. All right, so that determinant is 0. That determinant is 0. That determinant is 0. So is my answer 0 over 0, comma 0 over 0? No. No, my answer is, first of all, there's no unique solution. There's no unique solution because this was 0. Turns out this is a dependent system. Cramer's rule told me it was a dependent system. If it's a dependent system, then all of your determinants are 0. Now, These lines are no longer multiples. Now they're parallel, aren't they? If I put them in slope-intercept form, it'd be more obvious. They have the same slope, different y-intercepts. These are now parallel lines, so I know there's going to be no unique solution and there's going to be no parameterized solution. Do you agree this is an inconsistent system now? So how does that change?
dx and dy will be non-zero.
Well, first of all, I'm going to put 8 now. Secondly, either one of these are 0. 24 minus 16, 8 minus 12. So now it gives the illusion, oh, everything's fine. X is 8 over 0 and y is negative 4 over 0? I think not. An inconsistent system, by the way, remember what we said at the beginning? If the determinant of the coefficient matrix is 0, you do not get a unique solution. I didn't say you parameterize, I didn't say it was inconsistent, I just said you don't get a unique solution. So now using Cramer's rule, you can see, okay, when we had a dependent system, this was 0, but so were these. This is an inconsistent system, this is 0, but these are not. That's how you know. So if you were doing Cramer's rule and your determinant of the coefficient matrix is 0, you know it's not a unique solution, but you don't know if it's going to be dependent or inconsistent until you find the other ones. Okay, does that help? That, by the way, we don't dwell on this. Cramer's rule is a really fast, handy way to solve simple problems. I think on the next quiz, I think I asked you to do a 3x3 using Cramer's rule, and all of the numbers come out really nice. It's, you know, and the other thing is, of course, at the end you're going to check your answers using your calculator. Okay, this is kind of cool. It's an now. Why would we use Cramer's rule? We have so many more powerful methods. No, you're understanding what the computer is doing. The computer is using Cramer's rule. You're not using Cramer's rule. You're doing row operations on the matrix because you're fast. And fractions don't intimidate you if your answer is fractional. In fact, you even know how to avoid fractions until the last step of the problem. A computer can't strategize. It just has to go in a certain order that it's programmed. There's an algorithm it has to follow. It doesn't get to strategize. Oh, but if there's a 1 over here, let me grab it and switch things. No, it has to take its pivot. Where you can really mess up the computer is to start your matrix with an upper left position of a 0. That one really, computers don't like that one. If you're doing row operations, because it can't make it into a 1, and row switches are not part of the algorithm that you teach. It's using a 1 and then putting zeros. So that's one of the other reasons why Cramer's rule is so useful. Then it doesn't matter what numbers are in what position. Okay? So, the last of the applications, and might be the biggest one, we're going to use determinants to learn how to find inverses of matrices, but bigger than 2 by 2. I know how to find a 2 by 2 inverse. That's really, really easy. Right? I rearrange things and that kind of stuff. But now I'm going to go back and talk about something. We're going to introduce something called a cofactor matrix. Okay? Remember I said in every single matrix that exists, even non-square matrices, every position in the matrix has a minor that is associated with that position. Okay? Remember, the minor is all of the numbers that are left when I block out the row and column that my thing lives in. But for the purposes of finding an inverse, I need my matrix to be square to begin with. So we're only going to consider a square matrix right now, because it doesn't really make any sense to talk about non-square matrices. You know, sure, there are properties that hold over because the definitions are the same, but I want to talk about a non-square. So let's keep it simple. Let's just start with a 3 by 3. Okay? What I'm showing you for the 3 by 3 will extend to higher. And I've mentioned this before. What's true for a 2 by 2 is usually not true for anything bigger. But what's true for a 3 by 3 is probably true for everything bigger for the most part. Okay? Determinants, inverses, everything. We see that it's a different animal. Now, the minor associated with A11 would be this guy right here. The minor associated with A13 would be this little section here, and so on. There are 9 positions in my matrix, so therefore there are 9 minors. I want the determinant of every minor. Yikes. And rather than physically find each determinant, I'm just going to give it a symbol. Okay? Let's call Cij the determinant of Aij's minor. How's that? So C11 would be the determinant of that guy right there. Does that make sense? So if I said, what's C32? It'd be the determinant of those other four guys, and so on and so on and so on. We will do this with specific numbers. But before we do specific numbers, we need to know where everything goes. So we're going to call it capital C for cofactor matrix. C11, C12, C13, C21, C22, C23, C31, C32, C33, almost, not nothing. Finding each of the C's should be trivial because they're just 2 by 2 determinants. Okay? You with me on that? But when I'm doing determinants, doesn't the position within the matrix matter for plus and minuses and stuff? Yeah, and it still does matter. Oh, so what I'm going to do is put negatives on the positions that are negative. It could be there, 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 and there. Okay? Now, there is one more piece of the puzzle before we're done with this part. Now, a couple more pieces, all right. I have matrix A, it's 2 by 2. I want to find the cofactor matrix for A, which seems a little weird. Why? Because it can have 1 by 1s. Well, the determinant of a 1 by 1 matrix is simply that value. Those of you who had Calc 3 with me. Then when we did the Jacobian of the minors, and I showed you guys that the Jacobian comes from the chain rule factor, and we did all this. And so when you have one variable, your chain rule factor is one term. When it's two variables, it's the determinant of a 2 by 2, 3 variables. I showed you guys that the Jacobian of the transformation, which is the determinant of the matrix of the transformation, is the chain rule. That's one of the most important results in all of calculus. It's the one area where linear crosses over. But where it gets a little bit wonky is that what if you only have one variable? Then you're technically talking about a 1 by 1 matrix, and the determinant of the 1 by 1 matrix is that one entry. That doesn't contradict anything. But usually we define a determinant starting at 2 by 2. But I have to be able to talk about a cofactor matrix of the 2 by 2. So what is the minor associated with A? Just the number D. Oh, okay. What's the minor associated with B? C. With C? B. And with D? A. Now where do the negatives go? Plus, minus. Starting to look a little more familiar? Except it's not exactly the same, because what do we know about the 2 by 2 inverse? Isn't A inverse, we know it's 1 over the determinant of A. I'm going to write it like that. We know that. But isn't it dA negative B negative C? That's not the same thing as this. What is this matrix related to this one?
The transpose.
It's the transpose. C transpose is called the adjoint of A. We're starting with an n by n matrix. We're starting with an n by n matrix that actually has an inverse. If it doesn't have an inverse, then we're kind of wasting our time. That's like saying I'm going to try to solve a system that's inconsistent. We're really wasting our time. We can't go anywhere. Let's assume we're starting with an n by n matrix that actually has an inverse. Then A inverse equals 1 over the determinant of A. I've seen this movie before. Times C transpose. You're going to like this. Everybody likes this. For 3 by 3. Probably not for 4 by 4, but for 3 by 3. And now the 2 by 2 rule is exactly this, isn't it? If I do 1 over the determinant times the transpose of this, that's exactly the 2 by 2 2 by 2 inverse we derived. All right? Let's suppose A is, I don't know, 3, negative 2, 1, 4, 5, negative 6, negative 1, 3, negative 2. Okay. Let's start with the cofactor matrix. You can just do this. You don't have to do, 9 determinants off to the side. You're doing 2 by 2 determinants. Negative 10 minus negative 18, so that's negative 10 plus 18, that's 8. Negative 8 minus 6 is negative 14, but it's in a negative position, so positive 14. 12 minus negative 5, that's positive 17. Okay. 4 minus 3, negative 6, oh, I'm sorry, plus minus plus minus. Let's not forget that, okay. Negative 6 minus negative 1, so that's negative 5, it's in a plus position, so I don't change the sign. 9 minus 2, that's 7, but it's in a negative position. 12 minus 5, that's 7. Here we go. Negative 18 minus 4, that's negative 22, but it's in a plus or a negative position. 15 minus negative 8, that's positive 23. Do you notice I didn't use the number that was in that position at all, did I? I only looked at its minor. The number in that position is showing up in everybody else's minor. That's C. Okay? I need now the determinant of A. You're going to like this. How could that be the determinant? Don't I have to break it up and don't I have to multiply 3 by its minor determinant? That's what that number is, it's determinant. And don't I have to multiply negative 2 and then change the sign times this? But it's already been taken care of, it's sitting right there. You see? Isn't that nice? So finding the determinant now, we've already done all the heavy lifting. Pick any row or column, I went with the first row. If I pick any row or column, I should get the same answer. So what's this? 24 minus 28 plus 17, that's 13. So far, so good? Regardless of how we do this problem, right? See what I'm going to do it the long way. Negative 10 plus 18, that's 8. 8 times 3 is 24. Now I'm going to go negative 8 minus 6, that's negative 14 times negative 2, that's positive 28, but it's in a negative position, so now it's negative 28. 12 minus negative 5, that's 17 times 1. It's already right there. We've already done all the work. But I needed the cofactor matrix. Times what matrix? The transpose of this one. Now, is it possible we got one of those numbers wrong? Is it possible we got several of those numbers wrong? Yeah. The first mistake that most people make is they forget to put the negative signs. They forget to do the sign changes because of position. Okay, I really want to know if I did this right. I don't want to multiply the 1/13th in yet, because I'd like to check my answer. Wouldn't you rather check the answer without the 13ths? Yeah. How do I check it? Multiply these together. Does it matter what order I multiply them together? No. I'm either going to get the identity or I'm not. All right? So I'll go this way because it's right. 24 minus 4 minus 7. Well, 1/4 minus 4, that's 13. Times 1/13. Oh. So I'm looking for 13s, not 1s. Agreed? Because I'm multiplying by 1/13th after the fact. Ah! Negative 16 minus 5, that's negative 21, plus 21, that's 0. 8 plus 6 minus 14, that's 0. Good start. 42 minus 20 minus 22, that's 0. Negative 28, negative 25, plus 66, that's 13. That was good. 14 plus 30 minus 44, that's 0. 51 minus 28, that's 23. Minus 23, that's 0. Negative 34, negative 35, plus 69, that's 0. 17 plus 42 minus 46, that's 13. Did I do it correctly? Yes. So now what are you going to do? You're going to put the 13s in there. Now, I have an inverse where every number is something over 13. Yuck. Where did you work with a fraction anywhere in this problem, or did you? You didn't. Could you have done this problem perhaps even faster than the standard row operations? For most people, it's at least a tie. And some people, if you're fast at the calculating the little 2x2 determinants, you can actually do this one faster. And you never dealt with a fraction anywhere in the problem, you only recorded your final answer. Now, if this were a 4x4, you wouldn't want to do this. It takes too long. Think about your minors. They're all 3x3s. Ooh. And you'd have 16 of them. Ooh. That's the problem. You'd have 16 3x3 determinants that you'd have to calculate. Would that be fast for anybody here? Probably not. So all of a sudden, it's not a great idea if I had a 4x4 or a 10x10. But the fact is, my final answer, every one of these is over 13 in the end. I'll move that in. And I have a matrix of fractions. I want to do this on a computer, and I want to augment my matrix with the identity matrix and do row operations until I have an identity on the one side. That means there's no way around it. I'm going to have to multiply by fractions, which means the computer's going to store decimals, which means my inverse is going to be all decimals. Except maybe that's not a way the computer does it. This is how the computer does it. It's the only way to preserve the fractions. Do you see any fractions in the process? No. Only the final answer. I put it back in. The reason that we learned this and this method exists is this is not efficient by hand if it's bigger than 3x3. It's not. There's too many determinants to take. But I did a 3x3 so you could see what went on. And a great many of you will actually say, I'm probably faster this way than the standard way. Because there's just more mistakes when I'm doing row operations and I start introducing fractions. So it's beautiful. But if I'm doing this on a computer and I'm trying to preserve the fractions and I don't want decimal values, then you'd use this method. This is called finding the inverse using the adjoint. I kind of wish we just said finding the inverse using the cofactor matrix. But the adjoint is the transpose of the cofactor matrix. And you're not actually using the cofactor, you're using its transpose. So that's why we use a different term there. Yeah, question?
What is the definition of adjoint in the first place?
I'm sorry, pull that.
What is the definition of adjoint in the first place?
That's what I just said. That's the definition of the adjoint. The transpose of the cofactor matrix. That's it.
Do you mean the word adjoint? Do you mean the word adjoint?
I don't know any other use of this word other than this. I'm sure that's out there somewhere. It's one of those words that might have multiple meanings in a different context, but in a mathematical context, it just means this. That's it. So when you're looking and you say use the adjoint to find an inverse, you know that involves the cofactor. But it's not the cofactor, it's its transpose. So there's a couple of places we make errors. The obvious one is we go too fast in calculating 2x2 determinants. Those are supposed to be easy. But you're doing 9 2x2s. Is it possible you could make an error? Yeah, and you can't just keep redoing it. You got to know. How do I catch my error? When I multiplied these out, that's where I catch my error. If it doesn't multiply out, then I know I have an error, which is kind of a pain. But think about it logically. Once I found this guy here by finding all of my little determinants, writing its transpose didn't require any work. I'm not going to multiply this matrix. I'm going to multiply this matrix by my original matrix. I either get a multiple of the identity or not. Now, as a rule, I'm going to tell you what you do get, always. If you multiply A times this, you will get you multiply A times the transpose of the cofactor matrix, the adjoint matrix, you will get a diagonal matrix with the determinants on the diagonal. That's what we just did. We got all 13s, remember? So in other words, you get this times the identity. Oh, that's why if I multiply this by 1 over A, it turns out to be the inverse, because now A times 1 over A cofactor is now the identity. That's why. So your check, don't use the 1 over in your check. Do your check this way. It's a lot easier. If it multiplies and you get the right thing, then you know you're correct. But you never had to deal with a fraction. Now, let's suppose I have to do this problem. I have a really large matrix. And I'm told to find the inverse, and I'm told to maybe solve the system using the inverse, whatever. I need to find the inverse. And I have a decent calculator. You know, I have a 5 by 5, let's say. Could I use the calculator to find the cofactor matrix? Like, I don't know if your calculator has a function called, for cofactor. But worst comes to worst, could I enter, all the minors and then have the calculator calculate the determinants? Yeah, it would be very, very time consuming, very inefficient, but you could do it if you had to. You wouldn't want to do that by hand. You don't want to do a 5 by 5 inverse anyway by hand. It's just too long. But understand that the role that technology can play, it's doing things that you wouldn't do because it takes too long by hand to do some of these processes, but we're preserving integer values in numerators and denominators. That's the key. I want to preserve integer values so that I can state my answer as just the quotient of these integer values rather than decimal approximations of those. And what we know is that if we go decimals early and the computer's rounding things off, then it's using the rounded off value. It doesn't store the real number all the way, it just stores the rounded off value. That's where you can get a little bit off. And that's why I said for years I'd be teaching linear algebra. I'd give a simple problem. I'd give problems where the answer was 1, 2, 3 on purpose. And everybody used a calculator. I got things like 1.04, 1.97, 3.06. That would be a typical answer, because that's what the calculator gave out. But it was integer solutions because I started with a pivot of maybe 7. Oh, so mean of me. So the first step, the calculator multiplied by 1/7 and only stored 2 decimals, which meant that every decimal was wrong in the second decimal place on your first step, and a lot of them were even wrong in the first place. Yeah, it just... So somewhere down along the way, I started teaching this, right after Professor Gauss gave me permission to share his material. That was before or after President Lincoln. I forget sometimes. It's been a while. So yeah, I'm not doing it on. Just you guys didn't know that, did you? Aragorn, Lord of the Rings. My kids, ever since they were little, they'd always tell their friends their dad was 87. For every year, I was 87. And it was classic. They just tell me, oh, yeah, my dad's 87, and you get more compliments that way. You look good for your age. I get a lot of that. So anyway, I've been doing this for a long time. I was doing this long before there were any computers programmed to do this. So we had to do everything by hand for a while. Somebody was asking me the other day, well, what did you do about this and this and this? Why didn't you just Google it? Why didn't you just look online? I was here long before the existence of the internet. ESPN was around for a generation before the existence of the internet. Yeah, that hasn't been around forever, believe it or not. And so there were certain things we had, do the hard way. Of course, yes, I walked barefoot in the snow, uphill to school and uphill home, like your parents did. All of us did. Tough and jam. People laugh like, no, there was no, graphing calculators were the worst things ever invented. First several years of graphing calculators, they couldn't get anything right. They were so bad. It took several generations. Literally took 10 years of trial and error before the graphing calculators could actually give a graph. You know how I know? Most anything you asked to graph, there was nothing to the left of the y-axis. They couldn't handle negative inputs. When you wanted to raise a negative number to an integer power, it would give you an error. Forget trying to take an odd root of a negative number. That was automatically going to be an error. It took a long time to get it right. They kept making them better and better. But when the graphing calculators finally were able to do matrix operations, I rejoiced. Because then I had a way I could check things. But for a long time, I couldn't even try to do a matrix problem on a calculator. I knew I was going to get the wrong answer. I could do it by hand so much easier and more accurately, and you can check your answers so easily and accurately. So, if nothing else, what are some of the applications we can do with the determinant? Points on a plane, I can determine collinearity or not. Points in space, I can determine coplanar or not. You're really not going to use the determinant to find the equation of the line and plane. You already know algebraic techniques that are very fast, very efficient, and very correct. But to determine if that point is on the line or that point is on the plane, way faster using the determinant. Not even close at that point. Now, flip side is, what if they're not collinear and the 3 points on the plane? We know we can find the area of some shape. I have 4 points in space. Now, in Calc 3, maybe not you remember this. If I have, oh, let me draw a picture. This is one that's fun. I have a few minutes. This is one of my favorite formulas to derive. Because nobody ever derives this, they just tell you the formula and they don't tell you the why. All right. I have 4 non-collinear points. The simplest two-dimensional shape that exists is a triangle, because you only need 3 distinct points to describe it. The simplest 3-dimensional shape that exists is this one. This is called a,
Pyramid.
yeah, more specifically, it'd be a triangular pyramid. Careful, because the base would determine it. There's an infinite number of pyramids that are different shapes. 4 sides.
Tetrahedron?
Tetrahedron, good. Tetra is 4. Okay, this is called a tetrahedron. The volume of a tetrahedron? Ooh. Well, we do know a few things. We know how to find the volume of a prism. Agreed? It's area of the base times the height. You also know how to find the volume of a pyramid. And we derived this in Calc 1 using the volume by slicing. Do you remember what the fraction is? A pyramid with the same base and height as the prism, 1/2, 1/3. Same as a circular cone versus a circular cylinder. We know the volume of a pyramid is 1/3 the area of the base times the height. And again, we actually prove that in Calc 1 when we do the volume by slicing. I do it in my class. Not a big deal. So, the most common mistake people make is they want to put a 1/2, not a 1/3. And so here's the way I like to explain it using simple geometry. I have a rectangle, base times height. I know that. I have a triangle that's inscribed in the rectangle, same base and same height. I know the area of that triangle is 1/2. So if I have a triangular prism, so think of extending this out that way. A triangular prism, remember the definition of a prism is parallel congruent polygonal bases and the lateral sides are rectangles. They're orthogonal to the base. That's important. If they're not orthogonal, it's this. Okay, this is called a right prism. That's called oblique. And we tend to stay away from that one because it's harder to work with. You know, if we had the oblique structures, that would be bad. You know, that means the floor above us won't stay above us for very long. So we tend to go with right. That literally means that your lateral faces are at right angles with your, you know, floors and things. So I want a triangular prism. We know the volume of that because the area of a triangle is 1/2 the area of the rectangle. So the volume of the triangular prism that fits in here we know is exactly 1/2 the volume of the room. So I've done this in Calc 3. Some of you've been in those classes. We're going to have the first ever Calc 3 sleepover. We're going to do it here. So I got a gigantical tent, one of those military tents. The tent's going to completely cover the floor. It's going to go up to the ceiling and it's going to do this. So clearly it's a triangular prism. Do you agree? So we know the volume of that tent is exactly 1/2 the volume of the room. It's definitely not this. It's way bigger than this. So right after the first ever sleepover, we're going to do the only logical thing. We're going to fill the tent with Jell-O. It's a sealed tent. So we're going to make a Jell-O mold, then we're going to get rid of the tent. Now we have this gigantical Jell-O mold. And several of you have already put in your request, I want some of it. So what we're going to do next is, I'm going to go up to the center of the room and I'm going to slice off a portion of that Jell-O mold in both directions. I'm basically removing 1/12 of the Jell-O mold in both directions. Now we'll have a rectangular pyramid. Agreed? And we know the volume of that pyramid is a third the volume of the room, whereas the triangular tent was half. Now I got this pyramid. Beautiful. How do I get this? Oh, I erased it. How do I get my tetrahedron? So Stephen and Matthew were both, arguing and fighting. They both bribed me sufficiently, but you gave me the same size bribe, so I'm going to do the whole King Solomon thing. I'm going to split the Jello mold in half, right down diagonal. What shape do each of them get? Tetrahedron. The tetrahedron is exactly half the rectangular pyramid. But if the rectangular pyramid's volume was 1/3 of the prism, then what is the volume of the tetrahedron? 1/6. A lot of you have seen that formula but had no idea where the 1/6 came from, and I can't do that using calculus. I can only do that using geometry. So the volume of the tetrahedron is 1/6 the volume of the rectangular prism that it occupies. Okay? I gave you 4 non-coplanar points in space. Don't they uniquely determine a tetrahedron now? So when I say, what is the volume of the, not rectangular prism, because I may not have right angles. So if I have that 3-dimensional guy with the tilted things and it's 3-dimensional, there's another name, it's the goofiest.
Parallelepiped.
It's a parallelepiped, and that absolutely sounds like a made-up word as far as I'm concerned. A parallelepiped is like the prism, but it means your lateral faces are not necessarily rectangles, but they're at least parallelograms. Oh, okay, so think of this. I've got my tilty room with everything's a little bit off, but the volume of the parallelepiped is still the same thing. It's the area of the base times the height. See, I don't take that length, I take the length, because the area of a parallelogram is the length of the base times the height. Not the length of the side, the height. So it's a similar formula. So the tetrahedron that fits in the parallelepiped is going to be 1/6 the volume of the parallelepiped. So if I gave you 4 non-collinear points in space, non-coplanar points in space, and you determine they're not all on the same plane, they will uniquely determine a tetrahedron, they will uniquely determine a parallelepiped. The value of the determinant, plus or minus, would be the volume of the parallelepiped. I'd need to take 1/6 of that absolute value to get the volume of the tetrahedron. Does that make sense? It's kind of an obscure formula, but it can be very, very useful, right? Construction, engineering, all that. And stop. All right, we have official